Welcome back to See the Pragna channel. This is our second episode, and in this episode, we are diving deep into how data really moves inside modern organizations. We will explore the world of data pipelines, workflow orchestration, and stream processing, and break down exactly how tools like Apache Kafka keep the data flowing at scale. Let's start simple. Let's not make it complex. At the heart of data engineering, what do you have? You might have heard about this. It's called data pipeline. Think of this as the highway system for your organization's information. And you have already seen the example of it where we had a DB database, let's say A, and then you had an ETL job, and then you had your data warehouse. We showed it this in the previous episode, right? And this will have extraction, transformation, and loading. It starts by connecting to a database. Then the first step is extraction, like maybe like running a SQL query. And then the second is transform, clean, reshape, enrich the data, maybe convert data types, fill in missing values, or assign naming conventions. And third is the loading, writing that ready to use data into a central destination. This is the basic but essential flow of an ETL pipeline. That's it. This is an example of a pipeline. But real world pipelines are rarely this simple, isn't it? It's like in your school, when math teacher or any teacher explains you something, it sounds very easy. Oh, that's it. But when they give homework or when they ask a question in the exam, it's completely different, isn't it? We have already, most of us have seen that. Now imagine you don't have one ETL job, but you have whole network of jobs that need to run in a specific order. Correct? If this is this simple, it would be nice, but it's not. But if you have plenty, when you have plenty, you would this won't work out. So you would that's where the workflow orchestration comes in. Got it? So how does that look like? It looks something like this. That's cron process, and then you have pipeline job A, then you will have pipeline B, and let's say you have a pipeline C, and then you have pipeline D, and then you have, let's say our target is a data lake. Correct? And as I said, previously we had only one pipeline, but see, you in this flow you have three or four pipelines. And this pipeline A might to have a source, transform, and then sync. Same thing, source, transform, sync, source, transform, sync, source, transform, sync. What is a cron process? A cron process, or usual a scheduler, this kicks things off. So basically what this does is you will schedule it maybe every hour or every night, or in response to some other event you want to trigger your pipeline. Trigger, trigger, trigger. Okay. Then you have pipeline A. This is reading from a source, then transforms the data and writes it somewhere. This is called the sync. When job A finishes, it can trigger pipeline job B, which might process the data further. The pipeline A can branch out to B and C, and they can run in parallel or even trigger additional jobs downstreams, as you can see here. Finally, all these jobs might culminate in loading the data into a data lake. This structure forms what's called a DAG, directed acyclic graph. In short, DAG. Tools like Airflow. This is a famous tool. We will use this tool in one of the examples somewhere, but you need to learn this. This tool or tools like this are built to manage these kind of workflows, making sure each job runs in the right order and only when its dependencies are met. Now you might be source, you might already know where your data comes from, like upstream rivers. But what is a sink? Sinks are where your data ends up, like downstream lakes or oceans, right? You call them as sinks because water comes from somewhere. Like if at India, then you have Himalayas, water comes from there and ends up in other rivers. Ganga, Saraswati, it's not there now, but it used to be. Think of data moving through these pipelines like water flowing through a network of streams and rivers. Each step collects, merges, or splits the flow until it eventually ends up in a data lake or data warehouse. With pipelines this complex, I mean, this is also, I would say, it's a medium one, it's not a complex one. I have seen crazy pipelines. How do you keep track of everything? Correct? That's where a data catalog comes in. What comes in? A data catalog. A data catalog is what? It is a living inventory of all your organization's data. But what does it contain? It contains the source. What does that mean? It means where each data set lives, in which folder, etc. And who owns it. Those are called data stewards, people who own the data. And it contains what fields and format it contains. And then what rules govern its use. They are part of governance and access policies. And crucially, it contains the lineage, the full history of how each dataset was produced and transformed. Now, again, we are hearing lineage for the second time, but why does it matter? Why does lineage matter? Because it helps you, lineage, it matters because it helps you trace errors, reproduce results, and meet compliance requirements. If something goes wrong, you can always track the problem back to its source. That's why lineage is very important. Now, what if your data isn't just coming in periodic batches like every hour or every night? But what if it is flowing real time? This is where streaming, not streaming, stream processing, you can call it, or streaming, anything, both are comes into picture. Let's quickly cover the basics because streaming is also important. Early systems let processes inside one machine talk using a method called pub sub or publish subscribe. What is it? Publish subscribe. Engineers took this pattern and made it network. Now, different servers could communicate by sending messages into queues, kind of like a group chat for computers. But as systems got bigger, there was a new challenge. How do you make sure you don't lose messages if something goes wrong? And how do you make sure multiple consumers can process the same data at their own pace? Not when you give, instead when they want. That's where tools like Kafka changed the game. Well, how does it work? Well, let me show you a real diagram, then you will understand. We have a, let's say, producer A. And then in the producer say, let's say we have a topic called user events. Topics are just think of them as folders where you have your data, and it is partitioned into four. Okay, so this is producer. Then you have your Kafka architecture here. Okay, so you have your user events. User events, I'll just short topic, and then you have your Kafka cluster, and in the cluster you have broker A, broker B, and broker C. What is broker? What is producer? Hold on, you will learn every word you hear. This is a topic, and what topic is it? User events. And then you have again topic, user events, and finally you have consumers. I will explain you what is producer, what is consumer. Don't worry about it. And you have consumer A, consumer B. So this is a typical Kafka architecture diagram. So let's connect it to this, and then let's connect to this, and then let's put it to this and this, and finally this. Okay. So what is going on here? So you have producer. Producer is not the movie producer. You can consider it as movie producer as well. Producer is someone who makes stuff. As a movie producer, they make the movie. Here, producers are whoever is making the data, right? For example, or wherever you are getting your data from, like web apps, services, or devices. What do? They publish events to Kafka topics. That just means publish events to Kafka topics, like movie producers publishing their movie in the theaters. Got it? Imagine you have a user events topic. Imagine the movie's user events. Now, each topic is split into partitions to allow for massive parallel processing. Okay? Similar, if we take the movie analogy, imagine if you just play that movie in one theater, all the audience would be waiting in line to watch the movie, right? Instead, the producer decided to release the movie in multiple theaters throughout the country. So that's why because when you release in many theaters, people will go and watch in their local theater instead of coming to one theater and waiting in line for that. Similarly here, these topics, each topic is split into n number of partitions to allow for massive parallel processing. Now Kafka is run in a cluster of brokers, right? Um, which with each broker managing a set of partitions for high reliability and scalability. Maybe brokers are kind of like distributors. They might distribute the film to a couple of theaters in their place, right? Think of it as like that. Why these brokers manage these partitions for high reliability and scalability? And then you have consumers like audience, and in this case like analytic engines, real-time dashboards, or machine learning models. They subscribe to the topics and process events as they arrive. So these guys, producers publish, consumers subscribe. It's like subscribing is like back when you had newspaper magazines, you subscribes to yearly, then every month, if it is a monthly magazine, they give you one. Similarly, you subscribe to these topics, and whenever there is data in the topic, it is automatically sent it to you. Now Kafka, how does it do all these things? It uses a distributed write ahead log, meaning data is written durably and it can be replayed if needed. So let's assume even if a consumer failed when they sent the data or falls behind, it can always come back and read the data it missed. So you write it once, but you can replay it as many times as you want. This architecture is what makes Kafka the backbone of real-time analytics, event-driven apps, and modern data platforms. It is very reliable, scalable, and designed to handle data at internet scale. So, to recap whatever we learned so far, data engineers build and manage pipelines that reliably move and transform data at scale, and simple ETL jobs can grow into complex workflows coordinated by tools like Airflow. Then, data catalogs and lineage tracking are essential for managing complexity and ensuring trust in your data. And with real time data, technologies like Kafka are absolutely essential, letting you capture, store, and process events as they happen. Understanding these foundations is key for anyone looking to master data engineering and build truly modern, robust data platforms. And that concludes this episode. But wait a minute. In the previous video, I forgot to tell you something. At the end of each video, what will you have? You will have 15 exercise questions and 15 interview questions. Um, so right now I have them as PDF, but I'm planning to host them on a website. So by the time this goes live, you will have that website. So I will provide the website link in the description. You can click and go and do the exercises. And what are those exercises? They test how much you learn from these videos. And interview questions are on the concepts that we covered in the videos. So that will prepare you for the interviews as well. And when we get hands on, you are going to have classwork and homework. We'll talk about it at that time. But before moving on to the next video, I highly recommend you to do those exercises and prepare those interview questions. Got it? All right. That being said, I hope you enjoyed this video. If you did, don't forget to like, comment, and subscribe. See you in the next video. Peace out and love you all.